Hello everyone. Today in this session we are going to see the method 2 called as linear differential equation or Leibniz linear differential equation of solving differential equations. So the method is called Leibniz linear differential equation. So actually this is also a direct method to solve a particular form of differential equations. In this, what exactly we do? A differential equation in which dependent variable and its differential coefficients occur only in first degree and not multiplied by together, then it is called linear differential equation. We generally call the definition of linear differential equation is that definition here is a differential equation. I use a short form DE for all the time for differential equation. A DE in which dependent variable, you know that what is dependent variable? Dependent variable and its differential coefficients and its differential coefficient and its differential coefficients occur only in first degree. Occur only in first degree. Means degree should be 1 and not multiplied together and not multiplied together. So let us see how the form looks like. So let me take a form, a general form, dy over dx plus py is equal to q. Here, what is the dependent variable in this equation? Y is dependent variable. Y is dependent variable. So dependent variable and its differential coefficients. What is the differential coefficient? Dy dx. It is occurring first degree only. And order also 1. Here order is 1 and it is degree also a 1. So it is satisfying a linear differential equation definition and not multiplied by together. And y and dy by dx are not multiplied by together in the equation. So suppose if the equation is like this, y into dy by dx plus py is equal to q form, then it is a nonlinear differential equation. Because y and its differential coefficients are multiplied by together. So this condition is not satisfied. So it is nonlinear differential equation. But this is linear differential equation. You may ask like, what is the p comma q r here? In this, p comma q are functions of x. Any function, it may be exponential, logarithmic, or simple, sinusoidal, hyperbolic, whatever it is. P comma q are functions of x only. Functions of x only. Then the direct solution I am writing now. Direct solution is, it means if the equation is given in this form, dy by dx plus py is equal to q form, then the solution is y into e power integral of p into dx is equal to integral of q into e power integral of p into dx plus constant. It's an arbitrary constant, I told you. So this is that's it. If you solve this one, your solution is done for the given differential equation. But here e power integration of p into dx we generally call as integrating factor. E power integration of p into dx we call as integrating factor. Integrating factor. That's it. This is the actually basic theory behind this Leibniz linear differential equation. You should understand in this that in this definition two things. dependent variable and its differential quotients occur only in first degree, that condition should be satisfied. You know that what is the degree, and they should not multiply by together. They should not multiply together. It means y and dy by dx should not multiply together like this. So if this is the case, then you cannot solve by using this direct solution. If this is the case, you can solve by using this direct solution. Now straight away we will solve one problem by using this Leibniz linear differential equation method. So let's see. We go for phase 2. So solve the question is looks like this: e power minus 2 into root x over root x minus y over root x into dx by dy is equal to 1. Remember, by seeing this equation, you may think that we can solve by using method 1. What is the method 1? Variables separable method. Like you may that may be possible. Actually, they will not ask you directly. You solve this equation by using Leibniz rule. Sometimes they may give, but if they do not give that, you have to check whether it will fall under first method or linear differential equation method. That you have to check first. So anyhow, by using first method, you cannot solve this equation. You can try if you want. Y and dy terms and x and dx terms, you can try to separate. Even though sometimes there are equations you can separate it, but it takes long time. So you have to identify immediately what type of equation it is, and it will fall under which category. Is it variable separable method or linear differential equation method? Because we are seeing just 2 methods only. After seeing 10 methods or something like that, if you see a question, you have to identify under which method the question will fall. That method you have to execute to solve that particular problem. So now by seeing this one, you can try if you want. This is anyhow it's not possible by using variable separable method. So now I little change this equation. I change dx by dy. I will take right hand side, e power minus 2 root x over root x minus y over root x is equal to dy by dx. See, now it is looking little closer to this linear differential equation form or Leibniz form. Now I will write I do little modifications more. This term I will take that side, right hand side. So dy by dx, first right hand term I am writing, y root x I am taking that side, y over root x is equal to e power minus 2 root x by root x. So now you see this equation, it is exactly looking the Leibniz form. See, dy by dx plus p into y is equal to q. So p and q are functions of x, I said. So what is p here? 1 over root x. What is q? E power minus 2 root x over root x. So it is satisfied, and it is linear because the two conditions are satisfied by in this equation. So I conclude that it is coming under Leibniz form. So now what is the solution? What is the solution? We know that the solution is y into e power integration of p into dx is equal to integration of q integration into e power integration of p into dx plus constant. So firstly, by looking this equation, it may be little complex. So what I do is integrating factor. We know that e power integration of p into dx, that I calculate first. So integrating factor if is equal to e power integration of p into dx. So first let me solve that one. E power integration of p, what is the p? Here it is there, 1 over root x dx. So e power 1 over root x. What is the integration? Generally, this is also a formula like x power n. The integration of x power n is x power n plus 1 over n plus 1. If you do that, you will get 2 root x. You will get 2 root x. That's it. Integrating factor is done. So how it is come if you want to know 1 over root x integration of root x is x power n 1 by 2. If you take top, x power minus 1 by 2 dx. So you know that formula x power n is equal to x power n plus 1 by n plus 1. So x power minus 1 by 2 plus 1 divided by minus 1 by 2 plus 1. It means x to the power 1 by 2 by 1 by 2. 2 into x power 1 by 2. It means 2 root x. This is the way it came. So I just want to remove this. Just to make you understand how this 2 root x came, I have written this. So I'm deleting this one. So now, what is the next step? Integrating factor is done. So in the place of e power integration of p into dx, I can put e power 2 root x. I can put e power 2 root x. Okay. Now, so now I am writing this equation only again. Y into e power integration of p into dx. I know that e power 2 root x is equal to integration of q. What is the q value? E power minus 2 root x divided by root x into what is the integrating factor? This e power integration of p into dx, e power 2 root x into dx. So y into e power 2 root x is equal to e power minus 2 root x, e power 2 root x, a power m into a power minus m. It will become a power 0, it will become 1. So integration of 1 over root x will remain into dx plus constant. Don't forget this constant, every time you have to add. It is an arbitrary constant, I said. So y into e power 2 root x is equal to 1 over root x. We just seen answer is 2 root x, integration of 1 over root x plus constant. This is the final solution of the given differential equation. So this is what exactly the Leibnitz form of linear differential equation. So here also you see, finally you are getting y and x terms only. One arbitrary constant is added at the end. Why? Because it is order 1. So one energy storing element will be there. So one arbitrary constant will come. And your answer is y in terms of x only you will obtain. That is called a final solution of linear differential equation or Leibniz form of linear differential equation. Thank you one and all for watching this video.